Okay, so first thing we're going to talk about is what actually is a line. So using your straight edge, I want you to draw a little pair of axes. It does not need to be very big. And it's crossing at 3 and -3. And draw your line. So if you had to describe a line to someone who's never seen one, you might describe it as something that looks like a piece of thread, long and skinny. Like thread, a line has no thickness, so you can't measure how wide it is. The arrowheads on the ends of the line means that it goes to infinity, which means there's an infinite number of points on a line, and we'll revisit that in a second. Because there's an infinite number of points on the line, we can't measure a line. You can measure a piece of a line, but you can't measure the actual line itself. Now, the equation of the line that we've drawn on our little graph is y equals 2/3 x plus 2. And in this form, there are some special names. One of the special names is that the y variable is called the dependent variable. And dependent because it depends on the x. You have to actually calculate the y. You cannot just pick a y. You have to actually calculate it from the x. So it depends on the x, thus the name dependent. The x variable is the independent variable. Independent, you get to pick your x's for most processes. Now, independent and dependent are terms that you need in order to use a grapher, for example. So, and we'll revisit these more at a later time. But one of the biggest misunderstandings about lines is that a line is like a pencil or a pen. It's solid, right? It's like a bar. That's actually not the case. Way back in the 80s, some people decided to make a statement, and they lined up from, oh my goodness, it was like Washington to one of the Great Lakes. And that all these people that went camping, and on the day, they stood next to each other. And when you looked at the line of people from space, from a satellite, it looked like a straight line. You could actually see it from space. It was pretty cool. It was like Hands Across America, I think was the program. That is a little bit like what a line is. When you look at it, it looks like a solid line, but just like Hands Across America, it's not. It's actually a whole bunch of dots, like a whole bunch of people, standing so close together that you can't actually see between them. So really, a line is a whole bunch of points squooshed together. How many? Infinite, because those points can be any distance apart. They can be 0.5 apart, 0.2, 0.225, 0.1, 0.0005. They're super close together. So when we're talking about lines, you have to think of it as like a collection of points. All right, so tonight's assignment, we're not going to actually do graphing, but I do want to get the graphing conventions on your notes, just so you have them in case you need to refer to them. Graphing conventions are just guidelines so that the graph that you create is a good quality graph that's useful. And for lines, one of the things you have to do for a graphing convention is to draw a line. You need to find 3 what we call good points. Now you have infinite to choose from, but good points are whole numbers because we can't tell the difference between a third and a half on a graph. There's no way. But whole numbers we can tell because of the squares on the graph paper. And as well as being whole numbers, they need to be far enough apart so that when you try to draw your line through them, your line is accurate on the ends. If you draw them super close together, your line ends are going to be all over the place. As all graphs, you use a ruler. Your graph for class needs to be bigger than a Post-it. So if I can cover it up with a Post-it, it's too small. It's not an effective graph. So it needs to be of a decent size. You need to use the blue squares on the graph paper. I know it sounds funny, but people sometimes they just ignore the squares and freehand it. No, but use the blue squares. And then the last convention is, in general, if the axes go by ones, like 1, 2, 3, 4, 5, -1, -2, -3, all you have to label are the points, the 3 points that you use. You don't have to write all the axes labels out. If your axes though go by 2s or 3s, then yes, you need to label your axes with 2, 4, 6, 8, 10, 3, 6, 9, something like that. But if it's ones, yeah, just label your 3 points and you're good to go. So those are generally the graphing conventions that we're going to follow. And if you follow these, they will work for any teacher from here until you graduate. All right, let's hit the nitty-gritty. Roman numeral 2. Slope-intercept form of a line. And it gets its name because it has the slope in it. It has the y-intercept in it. So we call it the slope-intercept form of a line. Here's the magic formula. Y equals mx plus b. The m and the b must be lowercase. You know from yesterday that the m is a reserved letter for slope, lowercase m. The lowercase b, in this case, is the y-intercept of the graph. And anytime anything we do requires a y-intercept, I want you to use it as a point. So you'll have 0, comma, and then whatever that b value is. And you'll thank me later when we start doing other intercepts and you have to keep them straight. So the b is the number. The slope is what's attached to the x, does not include the x. So just looking back at our little sketchy graph, this was 2/3 x plus 2. 2 is the y-intercept. Here's your y-axis, and this is the number 2. So that point is 0, 2 because the y-intercept is 2. All right, so what are we going to need to do to put a random equation into this form? First thing, you're going to solve for y. And then on the right side, you put x's before numbers. And you guys have been practicing that already with our formulas. When you practice putting the x's before the numbers, this should come super easy because we've already learned it. Another way to say solve for x is y in terms of x. Again, we learned that in the last chapter. And a third way, which we will actually cover in this chapter, y is a function of x. So all of those mean the same thing. It means solve for y and put x's before numbers. As I said before, the most special thing about slope-intercept form is that the equation is unique. There's only one way to do it, which we like because it means you can check your work. There's actually a correct way to look at it. Okay, so that's the bulk of the information. What we're going to do now is I'm going to go over 5 examples. 2 of them are special lines, which seem to be the ones that cause the most grief. So I'm flipping over the paper. Okay, example 1. y equals negative 4x plus 3. And they want you to find the slope, m, and the y-intercept. So the first couple problems on your homework are going to already be in the right form, which is y equals mx plus b. If it's already in that form, you don't need to do any math. Just pull off what you need. So my slope m is going to be negative 4. Notice there's no x, just the negative 4. My b is 3, so my y-intercept is 0, 3. We're going to write it as a point. So that's the first couple problems. Just pull the values right off the equation. All right, example 2. 2x plus y equals 8. Okay, this one is actually in standard form. It's not in slope-intercept form. So in order to be in slope-intercept form, we need to solve for y. Well, use your solving steps. Add or subtract y left. It's left. Add or subtract non-y's to the right. So the 2x needs to move. So we're going to subtract 2x from both sides. You get y equals negative 2x plus 8. You got to put the plus in between. And yes, that is in the right form. So pulling off my information, the slope is a negative 2. The b value is 8, so my y-intercept is 0, 8. All right, we're going to go into special lines. There's 2 of them, but before we do that, are there any questions about how you're supposed to put these into slope-intercept order? Okay, let's get into the special ones. 2y equals 7. Okay, so to put this in slope-intercept form, you would want to solve for y. So solving steps, add or subtract y's left, it's left. Add or subtract numbers right, it's right. Go on to step 3, multiply by the reciprocal to get the y alone. So I'm going to multiply by 1 over 2 on both sides. And that gives me y equals 7 halves. Okay, the reason you know this is a special line is it has no x in it. So it is a special line. And this particular special line is the first of 2. This is a horizontal line. Horizontal lines have the equation y equals a number, and it does not have an x value. Horizontal line means it goes left to right. It's totally flat. Horizontal lines, because they're totally flat, they have no x-intercept. They don't actually cross the x-axis unless it's a horizontal line through the origin. Of course, origin crosses both axes. So what do we do then about the questions? So because you know this is a horizontal line, you know it has a slope of 0. For the y-intercept, the number here is where it crosses the y-intercept. So the y-intercept is 0, 7 halves. All right, that's the first of our special lines. Here's the second one. 4 minus x equals 0. First thing you're going to notice on this is, hey, there's no y. I can't solve for that. All right, so there is no y. That means it is a special line. This is our second special line. It is a vertical line. And a vertical line has the equation x equals a number. A vertical line goes up and down. And it has no y-intercept. So what do we do if there's no y? You have to solve for x. So let's do that. I'm going to subtract 4 over to the right. Negative x equals negative 4. To get the negative off the x, you multiply both sides by a -1. A negative times a negative is a positive, and I get x equals 4. That is the equation of my vertical line. So again, pulling from what we did yesterday, once you recognize this vertical line, the slope is undefined. And because it is a vertical line, there is no y-intercept, so your answer to that would be none. Because it goes up and down, it does not cross the y-axis. So over here on the side, draw yourself a little pair of axes. Special lines are really easy to graph because the information to how to graph them is already in the equation. You don't even have to run points. You know if it has no y, it's vertical. The x says it crosses the x-axis. The number tells you where, at 4. 1, 2, 3, 4. So you're going to draw a vertical line that crosses the x-axis at 4. There you go. And that's why you can see it's not going to have a y-intercept because it's vertical. All right, last one on the notes and then we're done. One-third x plus 2/3 y equals 2. I have heard what you've been telling me that we need more practice on the fractions because that's what we struggle with. So we're going to put this into slope-intercept form. To do that, we solve for y. So add or subtract y terms left, it's left. Add or subtract non-y terms right, got to move the x. So we're going to subtract 1/3 x from both sides. So that leaves you with 2/3 y equals -1/3 x plus 2. All right, y's are left, non-y's are right. Go to step 3, get the y by itself using the reciprocal. The reciprocal of 2/3 is 3/2. So put the entire right side in parentheses, put the 2 over its invisible 1, and we're going to multiply everything on the right by the same thing. You always multiply both sides of an equal sign by the same number. On the left, the reciprocals divide to 1. On the right, we're going to backwards distribute tops times tops, bottoms times bottoms. We get -3 over 6x plus 6 over 2. And of course, you need to reduce your fractions. So I can factor a 3 out of those, and I end up with -1/2 x. And 6 divided by 2 is a 3. This is the one and only one time you will see me not put the x on the top of a fraction. When you use this form, because the x is separate from the slope, it has to go to the side. Now you'll notice I've shoved it pretty much on the same level as the 1 because it is really still on top. But as far as format goes, the x goes next to the number, so those stay separate. All right, so the slope of our line is the -1/2. And our b value is 3, so my y-intercept is 0, 3. All right, any questions about our lovely fraction problem?